Okay, hello online class, hello in-person class. Today we're going to pick up where we left off on the PowerPoint. I think this class was maybe one slide beyond this, but I just kind of want to recap. So remember that, because we're going to go through the dates pretty quickly also. No, I want to go back. Hold on. Down here. There we are. Ptolemy. Here we are. So one of the things I want to point out is just how long it took us to get away from the Earth-centered part of the solar system, or Earth-centered model of the solar system. Ptolemy kind of brought this about in AD 141, very, very early. And then if we fast forward a little bit to where we talked about Copernicus, it was almost 1,500 years later. That Copernicus was like, guys, I really think that the sun is in the center and the Earth is orbiting with the rest of the planets. And so very quickly after Copernicus brought this up, we get a lot of different changes. We looked at this image yesterday. Here's your Earth-centered view, the Ptolemaic view. Here's your, I forgot the word, Copernican. Yeah, it's not Copernicus, it's Copernican view with the sun in the center. And one of the things that really made a lot of sense with this were the phases of the moon and the phases of Venus, which we wouldn't really see till later. But look at the next date. This is just like, I think Tycho Brahe was born 3 years after Copernicus died. And so things are going to happen very quickly here. We talked about Tycho Brahe being a precise observer. I think I mentioned to you yesterday in the video and in the lecture, the idea of parallax, which is if you take an observation during one part of the year, the Earth is on one side of the sun. If you wait a full 6 months and take an observation on when the Earth is literally on the other side of the sun, you should get a pretty large angle relative to whatever you're observing, or at least large enough where you should be able to calculate this angle and possibly calculate a distance. This is also how, there's not a great example of this. This is also how snipers figure out how far away their target is. In the military, you don't send a single sniper out by him or herself. You send out I forgot the word. Yes, a spotter. There you go. I was going to say a scout, and I was like, that's not right. You have to send out a spotter, and the spotter needs to be some distance away from the person that actually has the rifle. They don't know exactly the distance to their target, but they do know their location, and they know the spotter's location, and using a little bit of math and a map, you can triangulate that distance and have a much better idea of exactly where your target is at. And so there's a lot of real-world applications for this, not just in space and space observation. That being said, Tycho Brahe, they say that he didn't believe in the Copernican system, but obviously he had some sort of belief, or he wouldn't have been looking for this stellar parallax. And so he really tried to find it. He said, if the sun is in the center and the Earth is moving around, I should be able to see this angle. And he really looked to see it. And because he didn't see it, that kind of kept him from fully buying in to the Copernican system. I will note this is not really fully Tycho Brahe's fault. He was lacking some vital tools that would have helped him. At this point, there's still no telescope. There's still no very good working telescope. I don't even know if he had a telescope at all. He did have some advanced instrumentation. You can see in the picture here, he's got a large arc angle, so he can get pretty precise angles for the stars that he's looking at and make very detailed notes about the things that he sees moving across the sky. That being said, he wasn't quite able to observe that stellar parallax, and so he never really kind of got on board. And real quick, I want to show this video, if I can get this to end. I got it's like a minute and a half, 2 minutes. This little video kind of goes over the parallax and shows it in the same way that I said it.
Hills in the distance? If you have, you've probably noticed that while nearby trees quickly fly past the window, the mountains move much slower and in the far distance, the moon and the stars don't seem to move at all. As you move, objects closer to you, such as the trees, seems to shift position relative to more distant objects, like the mountains. This effect is called parallax. The size of this shift depends on the distance you travel along the road and how far away the trees are. The closer they are to the road, the bigger the shift. The same thing happens as the Earth moves around the Sun. Over the course of a year, some stars appear to move a very small amount relative to other stars. Like the trees along the side of the road, these stars are just closer than those that don't seem to move. Actually, all stars are moving through space, but much more slowly than parallax, so we don't notice. Now, if we measure how much a star moves when the Earth does one complete trip around the Sun, we can use this to work out this angle, called the parallax angle. If we observe a star when the Earth is at one spot in its orbit, and then wait 6 months for the Earth to move around the Sun to the opposite point along its orbit and observe the star again, we can measure the parallax angle. Since we already know the distance from the Earth to the Sun, we can now use this parallax angle and some trigonometry to work out exactly how far away the star is. This is really useful because it allows us to calculate the distance to nearby stars very accurately. This can then be used to check the distance measured by different methods to even more distant objects out in space.
Okay, the more distant it is, the harder it's going to be super accurate. But we still use this. And if you think about, if we go back to Tycho Brahe and look at the time frame that he's in, anybody flying airplanes at this time? No. So your ability to, even if you wanted to do like a small parallax, your ability to travel from one side of the Earth to the other is almost non-existent. First off, it's very perilous. Second off, even if you make it to the exact opposite side of the Earth, it's going to take you months and months and months to actually get there. And so the parallax is very useful even today, because if we build a giant telescope observatory, you're not able to move that. And your ability to build an exact opposite telescope on the other side of the Earth isn't going to help you either. And so you really want to wait for the Earth to get all the way around, take another view of the same thing that you're looking at, and try to work out the parallax angle. So this, even though he wasn't able to observe it and prove it, this idea of the stellar parallax is very important for us moving forward. So the next person they're going to come up with is Johannes Kepler, and you can see that their lifetimes even overlapped. And so very quickly we're getting important additions to the understanding of the solar system and how the planets move. Kepler is very famous. There's an awesome telescope named after him, the Kepler Space Telescope. He ushered in the new age of astronomy. And what he did was he gave us 3 laws. They probably weren't laws at the time. They had to be worked out. But these laws still stand today. And they make a lot of sense, and they helped us fully understand what was going on in the solar system. So the first law is that the orbits of the planets are elliptical. And he got this from doing very precise measurements, maybe even using some of the measurements from Tycho Brahe. But what he noticed was, as the planets orbit, or let's just say, you can't even observe the orbit, but as they're going through the sky, he noticed that at certain times of the year, the planets moved faster. At other times of the year, the planets move slower. If they're moving faster and slower, you're not going to have a perfect circle. This is obviously not a perfect circle, but I'm pretty proud of that. It's maybe one of the better circles I've drawn. If the distance is always equal from the sun, you're not going to have a speed change. So if there is a speed change, that implies that instead of having a circle, you have more of an ellipse. Now, we exaggerate this ellipse for effect, especially on one of the next slides. Know that they're almost circles. For all intents and purposes, if you look at it from above, it's going to look really close to a circle. But it's not quite a circle, and so it is technically an ellipse, slightly elongated. So that's the first one. Orbits of the planets are not perfectly circle. They are an elliptical. The second one, planets revolve around the sun at varying speeds. And those two kind of go together. And we'll see that in another slide. The third one, there is a proportional relationship between a planet's orbital period, so how long it takes to go around the sun, and its distance to the sun measured in astronomical units, or the distance from the sun to the Earth. And so this one's actually pretty interesting, and I'm going to turn the lights on. I'm going to grab this poster, and this is actually a pretty cool poster. I'm going to try to get it on the wall today with the heat gun. If you get a chance, come up and look at these blue boxes next to the planets. They have some really interesting information. So the planets closest to the sun are closest to the sun in the picture. Obviously, this is not to scale. But you have Mercury, Venus, Earth, Mars, Jupiter, Saturn, Neptune, Uranus. I guess it would go Uranus, Neptune. And then way out here, Pluto. First off, Mercury doesn't take very long to get around the sun. A year for Mercury is 88 days here on Earth. So it goes around pretty quickly. Less than 3 months and it's already gone around the sun. For Venus, it's a little bit longer, 177 days, but still less than an Earth year. Mars is almost 2 Earth years for 1 Mars year. Mars is 687 days. And so it takes Mars quite a long time to get all the way around the sun. You also have Jupiter, Saturn, Neptune, Uranus, Pluto. I want to talk about Pluto because this is actually pretty interesting. Pluto has a 248 year on Pluto, an orbital period of 248 Earth years. And so if you look up when Pluto was discovered, I don't remember the exact date. I'm guessing like 150, 170 years ago. Since the day we knew Pluto was a thing, it has still not gone all the way around the sun even once. And that will kind of play a role when we talk later, when they get to the Pluto slide, which it looks like they deleted, but they just saved it to the very end. They kind of talk about why Pluto's not a planet anymore, and we'll kind of touch on some of those reasons. But one of them is that there's a decent portion of astronomers who aren't quite sure that Pluto's always going to be around and be a planet. Another thing I'd like to touch on as a side note, just because I'm going to bring this up a lot during the year because I like it and it has some really good examples. There's a book series right now called The Expanse. It's still ongoing. They don't have all the books done. There's a nice TV show on Amazon that's filmed by the book series. I prefer the books to the show, but the show's pretty awesome. So in the show, there's an interesting little moment where, well, first off, let me set the stage. In The Expanse, humans have spread out. We live on Earth. We have a pretty big colony on the moon. There's several million people that live on Mars and have for generations and generations. We also have people living out in the asteroid belt in between Mars and Jupiter. And there's also some people that live on moons of Saturn and of Jupiter. So we're kind of spread out everywhere. And it's almost like a space political drama. And they kind of reframe things that we have today in our current political climate. Instead of people disagreeing on cultural differences, religious differences, or racial skin tones and differences that way, people kind of have segregated into groups based on where you were born and what your body shape is. And the idea is if you were born on Earth or Mars, you grew up in gravity, you look very similar to the way that we look today. If you grew up out here in the belt on a spaceship or on a moon with very, very little gravity, your body is very elongated. You're like 7, 8 feet tall. You have a lot of health problems because of radiation, lack of nutrition, lack of sunlight. There's all sorts of things, but it's a very visual difference. You can look at somebody and know what group they belong to, the same way race works today. And so they have different political allies. They have different groups. Obviously, the people that are on Earth think that they're the most important, and the people who live out in space kind of get the back burner. They don't really get much consideration. And so there's this guy who's a recruiter for probably not a very good moral group, but he's trying to kind of recruit this kid, and he says, "How old are you?" And the kid's like, "I don't know, 19." And he's like, "It's messed up that even our age is based on a planet that we've never seen and never been to. We tell our age in Earth years. He's like, if we went by Saturn, you would just be experiencing your first birthday. And it's kind of interesting to see that dynamic and see that things are very different depending on what part of the solar system you're at. A little side note, you can see that today here. When they announce what time a TV show is going to be on, it's 9/8 Central. They don't even have to put a designation by the 9. Where's the 9 for? It's for New York. They always say it that way. Like we care what time it comes on in New York. And then they have to give the second designation that it's going to be on here in Central Time because we're like an afterthought. And then obviously we don't live on the Pacific Coast, but they don't even bother telling us what time it's going to be on the Pacific Coast. And so it's just this kind of interesting thing, and you can see it in politics, you can see it in sports. The East Coast, where a lot of people live and is kind of the beginning of the country, that always gets the primary designation for what time it is, what time your shows are going to come on. They're much more likely to put a sports event in prime time on the East Coast, even if I have to stay up till midnight to watch it here. That's the way it's going to be because New York and Boston and the East Coast is just much more important than the poor folks in Texas. And so there's a lot of interesting political stuff in that book series and that show. If you're interested, I would probably recommend it. If your parents are okay with you reading and watching adult things. There's nothing real bad in there, but it's not necessarily a high school thing. So what was I getting about here? Oh, the orbital periods. Some planets take a very, very long time to go around the sun. That being said, let's look at this. Orbital velocity. I guess it varies a little bit. I was thinking that the outer planets would go much, much faster. Even though they have a longer way to go and it takes them a long time to go around, I would think that they go much faster. And actually looking at the orbital velocity, it kind of varies. Mercury's about 47, Venus is 35, the Earth is 29. And so the inner planets are going faster. The outer planets are going pretty slow. But it's not necessarily a direct linear graph. So that's interesting. I will get this up, and you should be able to look at this. I don't know if I can take a scan for the people online, but maybe I'll take a nice picture and post it online for the online folks. So we're going to move on. Kepler gave us these 3 laws. They're very important. We still use them today. Here's a kind of picture of the elliptical orbit. Like I said, this is exaggerated. If you look at it from above, it's going to be much, much closer to a nice circle. But think about gravity. So here's my planet. It's coming this way. As it's moving further away from the sun, and this distance is getting larger and larger and larger, the sun's gravity is pulling back on it. It's trying to keep it from going away out into space. And so you're going to be slowing down during this leg of the trip. And as you get to the very end, which is called your apogee, the furthest point away from the sun or whatever object you're looking at, it's going to be going the slowest, the very slowest. Then as you turn back around and head back towards the sun, even though you're not going directly towards it, you're getting closer and closer and closer. The sun's gravity is pulling you the direction that you're going. And so you're going to be speeding up during this leg all the way till you get to the shortest point where you will be going your fastest speed during your orbit. And so that's what Kepler noticed was you're going much faster in one part of the year than you are in another part of the year. Also, let me go back. We're not going to touch on it too much. He also has some pretty interesting, in that law, he has some pretty interesting observations about these sections of this elliptical. Notice that they have sections and they have them like highlighted. And so there's some pretty interesting math that equates each of these sections to each other if you get into the math of it. So very quickly also, you get to Galileo Galilei, which let's just appreciate that name. That is one of history's greatest names ever. That's just an awesome name. He supported the Copernican theory. He used experimental data. And although he did not invent the telescope, which is wrongly attributed to him sometimes, He was one of the first people to construct a very good one, and he kind of perfected the early telescope when he made his own. So he constructed an astronomical telescope in 1609, and he discovered all sorts of things. What Galileo discovered was really, really groundbreaking for space exploration and understanding. So we knew about Jupiter. We didn't know that Jupiter had moons. He discovered the four largest moons of Jupiter. He noted that planets appeared as disks, which they're not disks. They are round, or they are spherical, not round, that's a better term. They're spherical, but depending on how you're looking at them, depending on your telescope and what angle you're looking at them through the Earth's atmosphere, they do kind of get flattened out in certain directions. He noticed the phases of Venus. So just like the moon has phases, full moon, new moon, waxing, waning, he saw the same things in Venus. Every planet has that, especially from our viewpoint. There's always going to be a light side that's facing the sun. There's always going to be a dark side that's facing away from the sun. And depending on what angle it is from us, we're going to see more or less of that light and dark side. He also noticed some features on the moon, like the Marias and the Highlands, which we can still see today. He was the first person to see sunspots and see that there was dynamics on the sun. There were dark spots, there were lighter spots, there were things happening. It wasn't just a static light that was being emitted. I would have liked a little bit of notation down here to tell me exactly what's going on, but I can assume that this is Galileo's telescope, which is pretty awesome that it's been preserved and kept so nice over such a long period of time. But I assume that's his telescope, or hopefully a fairly accurate recreation of his telescope. Here's a copy of his notes, obviously not in English, but he kept very meticulous notes, and obviously some of them survived in some form or another. And so he was really a huge influential figure in space exploration and understanding. This was not a picture taken by Galileo, but this is what he saw for Venus. And so it looks kind of just like the moon. I mean, obviously you can't see features like you can in the moon, but you have a full moon. I guess this would be waxing. I don't remember which way is waxing and waning. We'll get to that in another slide. But you have your different phases of the moon all the way until you have a new moon, which, remember, a new moon is where you don't see any of the light. It's just like the dark moon. Let's see. Then you get to Newton. Newton discovered gravity. Never say invented, because gravity's always been around. He kind of discovered it. He proposed the law of universal gravitation, saying that gravity was a force that kind of exists everywhere between everything. Proved that the force of gravity combined with the tendency of a planet to remain in a straight line motion results in the elliptical orbits. And basically this is, think of like you've got a ball on a string and you're swinging it around your head. At any point in time, if you let go of that ball, or the string, if you let go of that string, the ball is going to shoot off in one straight direction. It's not going to continue to curve. It's not going to move any other way. It's going to go in a straight line. And that's what the planets would do if you just happen to kind of delete the sun, which is a crazy thing to say, but if we're in the Matrix and you just went into the code and deleted the sun, we would just shoot off in one straight direction. But gravity is always pulling us back. It doesn't necessarily stop our motion, but it's what's keeping us kind of tethered to that point of gravity, and we move in an elliptical or a circular pattern. A little side note, which I think is very interesting. I'm going to bring this over here so the online people can see. It takes light time to travel, right? Sorry, I just turned the lights on with no warning. It takes light time to travel. So let's say this is the sun, put an S here, and here's your Earth. Propose the matrix theory again. We go into the matrix, we delete the sun. No like huge explosion, we're not going to die or anything. But we delete the sun. It takes 8 minutes for light to travel from the sun to the Earth. So if the sun were to just somehow disappear, it would be 8 minutes before we knew that. We would live in like ignorant bliss for 8 minutes, still basking in the sunlight. And then all of a sudden the sun would go out and we would know that 8 minutes ago something bad happened and we probably aren't going to live a whole lot longer. The weird thing is gravity, now we know this. I don't think Newton knew this. Gravity is not instantaneous. Gravity travels the same way that light does. And so if we were to delete the sun for 8 glorious minutes, we would orbit around an empty point in space, still feeling the gravity of the sun, even though it's no longer there. And then right as the light went out, so would the gravity, and we would just continue out into space and meet our fate, unfortunately. Good news is that's not going to happen unless we do live in the Matrix, and then we've got bigger problems than that, right? So remember that gravity, we know now that gravity travels in waves. It's not an instantaneous thing, and it moves through space kind of in the same way that light moves through space, which is pretty interesting. Let's see, yeah. Here's the example. I actually took time to draw this in first period, and drew all this out on the board, and then I hit the next button on the PowerPoint. I was like, oh, that was a waste of time. So here's kind of an example of what he's saying. At any point in time, the planet's forward motion, and who's taking physics in this class? Yeah, if you're taking physics, this might look kind of familiar. Your forward motion goes out in a straight line. Gravity is kind of pulling you back in, and so that section by section, that kind of brings this curve about. And so this is your net motion, your forward force, or I guess your inertial force, plus the force that's acting on you, which in this case would be gravity. Okay, what major change did Copernicus make in the Ptolemaic system? He switched the Earth and the Sun. He put the Sun in the center. He put the Earth with the rest of the planets orbiting around the Sun. And why was this change philosophically different? I think that's kind of the same answer to both of the questions. It drastically changed the way we look at the solar system and our place in it. So the next one's going to be nebular theory. We're going to stop here for today, just to kind of run down and show you what the rest of the PowerPoint looks like. Nebular theory is the beginning of us talking about the formation of the solar system and the formation of the planets, how they came together, why we have so many planets, why they all go the same direction, why so many of them have moons. There's a lot to kind of go through there, but we'll go through it pretty quick. We talk about protoplanets at the very beginning. We have a couple nice images of the solar system. Then we actually get into looking at the planets themselves. We have two different groups, the terrestrial, the small, hard, rock-like planets, and the Jovians, the large, gaseous planets. And then we literally go planet by planet. They start with planetary impacts, meteors, comets, things that hit the Earth or the moon or some other planet, impact craters. And then we get to the moon. We talk about the moon because it's the closest thing to us. It's very important for us. Then we go to the other planets. Mercury, Venus, Mars, Jupiter, Saturn. And then at the end, Uranus and Neptune. Just so y'all know, I didn't used to do this. It really bugged me when people did this. I use the word Uranus. You should know that most people use Uranus. I'm in a high school though, so it's easier for me to get through things if I say Uranus and not Uranus. I'm not gonna lie, I chuckle too. It's just kind of objectively funny. But yeah, Uranus is what you're gonna hear me say, and just gloss right over that. But Uranus and Neptune are twins. They're very similar. And then at the end, we will spend a little bit of time talking about, they have asteroids and comets, but at the end of the PowerPoint, we will spend a little bit of time talking about Pluto and why Pluto is no longer considered a planet. And as I mentioned to fourth period in my Earth and Space class the other day, this could easily change. In the next 10, 20 years, you could see the scientists who disagree with this assessment kind of come to prominence and make some better arguments, and you could see Pluto brought back into the fold. But there's lots of different things. they do you talk about the size comparison. I don't think that's necessarily right. There are things bigger in this solar system that are not planets, but they're clearly not planets. Pluto, regardless of its size, does have a logical argument for it being a planet. And to be fair, the things that they use to disclude Pluto have never been applied to any other planet. Doesn't mean they're wrong. That is just maybe one of the reasons people are fighting back against it so much, because they're like, this is why Pluto's not a thing. And everybody's like, this has never been a thing before. Why are you using this category to kind of exclude Pluto? So we'll get to that at the end. We still do have a lot to go through for this PowerPoint, but like I said, we're looking at roughly a chapter a week, maybe a little bit faster because we got to work in tests and labs and stuff, but not too bad. So thank you for joining us, online folk, and we'll see y'all tomorrow. If I can stop the video. Mr. Bailey's not